Okay, let's complete the trio of examples, and we're going to do a tangent here because the other videos we've seen have been sine and secant. This is tangent. Now, how do I know it's tangent? Well, it's easy to know that this is going to be tangent because of the plus sign. But again, tangent, all these trig substitution forms involve a squared number and a squared variable. It doesn't have to be a perfect square. Right? A lot of times they are, and when they are, that's kind of a hint that it's probably trig sub, especially if there's a radical involved, but the squared number plus a squared variable. Okay, now this is not squared, it's to the fourth power, but remember, x squared squared is x to the fourth, okay? So what it says here in the instructions are to make an appropriate substitution, and what they mean here is to do something like u equals x squared, so u squared then is x to the fourth. Okay, if u is x squared, then x is u to the 1/2 or the square root of u. Dx would then be 1/2 u to the -1/2 du. All right, now I am ready to plug all this in. I've got an x. So what is x? X is u to the 1/2. So u to the 1/2 or the square root of u times dx. Dx is 1/2 square root of u du. Right, u to the 1/2, same thing as square root of u du. All right, and then in the denominator, I have the square root of 49 plus, instead of x to the fourth, that's u squared. So what you can see is going to happen here is the u's to the 1/2 are going to cancel. I have just a 1/2 in the numerator. I'm going to pull it all the way out and say this is 1/2 the integral of just du in the numerator now. Square root of 49 is 7 squared plus u squared. All right, so we can easily see now that this is going to be the tangent substitution. And so the squared variable, notice what it's got here. X is the squared variable. X equals a, the number that's being squared, times tangent. So u is our squared variable now. U equals the number that's being squared times the tangent. All right, that would make du, the numerator, is equal to 7 secant squared theta d theta. All right, just the derivative of tangent times d theta. All right, now I'm ready to make the substitution. So again, I'm going to do two parts. Part one is just the algebraic manipulation. Then I'll go back and show you get the same trig integrand if you use trigonometry to come up with this. Okay, so once I make the substitution, I replace u with 7 tangent theta. I'm squaring that because u is being squared, and that's going to give me 49 tangent squared theta. And then, like we've seen before, that 49 shows up in both pieces, so I'm going to factor it out. And when it factors out, obviously the square root of 49 is 7. It's going to cancel that 7 from the numerator. All right, 1 plus the tangent squared of theta. 1 plus tangent squared, that's a Pythagorean identity. Those show up in trig substitution all the time. That is secant squared. So we're going to replace that with secant squared. And notice now this shows up on the bottom and the top. If you take any value, like for instance, just so you can see it 9, and you divide by the square root of that number, you end up with just the square. It's basically like, 9 to the first divided by 9 to the 1/2 is 9 to the 1 minus a half. You're always going to end up with the square root of the numerator. So I can write this as just the square root of secant squared, which is because we're squaring and then taking the square root, the absolute value technically. And we saw from a previous example, the integral of secant is the natural log, the absolute value of the secant theta plus the tangent of theta plus c. And now, this is again why I do trig to begin with. You need to create the right triangle to get back to x anyway. So the substitution we made here was u equals 7 tangent theta. That means the tangent of theta is equal to u divided by 7. And remember that right triangle definition of tangent is opposite over adjacent. So that means the opposite side over here is u, the adjacent side is 7, and that makes the hypotenuse square the square root of 49 plus u squared. Right, once again, that was the original denominator. Right, once we made the substitution, it was the original denominator. All right, we need secant and we need tangent for this. Okay, so secant, remember, is hypotenuse over adjacent. The hypotenuse is the square root of 49 plus u squared. Adjacent is 7. And then, like we saw, tangent is opposite over adjacent. The opposite is u over 7. All right, so I end up with secant is square root of 49 plus u squared over 7. Tangent is u over 7. All right, but u, all the way back to the original, remember our original variable was x. So all the way back here, u is x squared. U squared is x to the 4th. Right, and then when we're doing these, that would be fine. I would be perfectly fine if you did that. But there are property of logarithms that say you can combine these into, the numerators, obviously that's just property of fractions. But there are property of logarithms that say that if you have a log inside a log, then you can take the log of the numerator and subtract the log of the denominator. And we have this minus 1/2 log of 7 that comes from that property of logarithms. And this is an arbitrary constant. Well, so is any arbitrary constant plus a constant is just another arbitrary constant. So if you call this like C1 all the way through here with your work, then what we can do and what is kind of expected if you click on view an example, my math lab will just let these two things kind of combine together into just a single arbitrary constant. And so it's very common to see it written just like that without the denominator. So if this denominator is common like this with these problems, you can basically just think of it like dropping it off. Just look at the numerators and let that be the form of the antiderivative. Okay, now with the just like the previous problems, what I want you to see is I'm going to get to the same integrand via trigonometric approach rather than this algebraic approach. So I would do the same thing, get to here. But now at this point, I would go ahead and make my right triangle, solve this for tangent. So tangent theta is equal to u divided by 7. All right, tangent is opposite over adjacent. So opposite is u, adjacent is 7. So that makes, again, this 49 plus u squared. And again, I'm looking at this back as 49 just to make it easier to see. So this is a number on top and the square root of 49 plus u squared on the bottom. So again, I have to do it with 7 instead of the u because there's not a variable in the top. There's du, but there's not a u up there. So 7 over the square root of 49. What tangent function is that? That's adjacent over hypotenuse. That's cosine. All right, and then du is secant squared. So when I'm going to this integrand right here, the one that I set up to come up with the substitution, I'm going to replace 1 divided by the square root of 49 plus u squared with, again, to get a 1 up there, I'd have to multiply by 7th. So this is 1/7 cosine theta. And then du we can see is 7 secant squared theta, d theta. And when you do that, you can see 1 cosine will cancel with 1 secant, the 7s will cancel, and just like we got before, we got 1/2 the integral of the secant function. Right? And we don't have the square root of the square, so we don't have to worry about absolute values. It's just the secant function. All right, and there's the procedure, there's the trig approach to get there, rather than that algebraic route that we took to get there, right? And that still required us to make the right triangle to do the back substitution once we did the integration, right? That right triangle has already been constructed for when I do it right here. Once I get the integral, I've already created the right triangle that'll tell me secant and tangent, and I'm ready to go. So anyway, that's the reason why I like the trig approach. The right triangle is already there for you at the end.